This is Lab 2, Drawing Electric Fields. I borrowed a lot from Michael Purdy's PowerPoint on electric field drawings and turned it into the lab. Let's look at the first sheet and see that we're using what is known as an Overbeck board that I modified so that I could use a voltmeter instead of the board itself. An Overbeck board is designed to put a plate on the bottom that's conductive so that I can measure the voltage between two terminals, with a sheet of paper put at the top that I can mark what the voltage is. You see how the wand has a point on the bottom where you have a measuring point, and on the top you have a pencil point that you can actually place inside so that you can mark each voltage dot. This is the construction. The two sides are, one side is positive, one side is negative, and you have the voltage between 6 and 8 volts. You also have it attached so the wand can read the voltage on the plate below, and you can record what that dot means above. If you looked at the PowerPoints on electric field mapping, you realize that the basic equation for an electric field is force over a positive test charge. This electric field will be external to the charge. A force will exist when the test charge interacts with the field. The field is a math construct, and we draw it mostly that way. And the electric field vector is tangent to the electric field line. I've listed the rules for drawing these lines of force, which are the paths the positive test charge would follow. You start on the positive, you end on the negative. You decide on the number of lines coming out of the positive. Those would be the number of lines going into the negative. We want to make sure the lines are evenly distributed over the surface of the conductor. We can establish equal voltage lines by putting the zero part to the voltmeter, to the negative, and the positive part to the wand. Therefore, we can set a value of, let's say, 1 volt, and we very carefully mark each 1 volt between the two electrodes. The lines of force enter, leave, and go through the equal voltage lines perpendicular. The voltage lines and the electric field lines must always be smooth. The electric field lines must be perpendicular to the equal voltage lines. The electric field will be tangent to the electric field lines and always point to the negative. So this is what the Overbeck plate looks like on the bottom. The conducting side is face up on the back side. In our lab, we cut the resistors out of the circuit. We're using a voltmeter. So on the left-hand side, this is how you would turn it upside down, remove the screws, put the screws in place, then flip it over, put a sheet of paper on the top. Okay, then you connect the two terminals and set the voltage between 6 and 8 volts, where the negative end becomes the 0 volt line. You insert graph paper. Graph paper is actually best on the top side of the board, and tape it down thoroughly so it doesn't move. You'll see that you've got a template that you can actually put over the two little pegs here, and then you can draw the pattern on the top. Then you very carefully slide the wand between the board, and you don't want to press too hard, but you do want to press enough to get good contact. Then you turn it on and you begin to look at what the pattern the voltmeter gives you. This is a video on my setup that we use to generate your work product. Please play it before we move along. You'll see me do the setup and do the beginnings of the drawings. Over here on the side, you'll see a picture of the Overbeck board with full setup, the Overbeck board with paper on top with the drawing, and the template card. This girl actually did what I said. She's placing the template on the board in the picture shown here, but we don't use a galvanometer. I think it's too crude. And the little plastic sheet is the template. Please watch her. She's a little soft-spoken, so you want to probably turn up the volume so you can listen to her describe it as she does it. Okay, well, now that you've got the voltmeter and you've got the dashed dots finished, so you've actually done somewhere between 10 and 20 dots per voltage, you can see a pattern of 1 volt, 2 volt, 3 volt, 4 volt, 5 volt. And so this is enough to actually do our drawing. So what we want to do with the equal voltage lines now is dash those dots, because that voltage line is continuous, but we don't want it to be solid. We want it to be dashed so people can distinguish between the equal voltage lines and the lines of force, our electric field lines. Okay. So this is the first step. We've got our dot pattern, we solidified them, now we're going to dash them. One end is negative, the other is positive. We've got our line set up. This is the first step. And you're going to see the first step is what you're going to be drawing on, and complete step 2, step 3 on a certified plate that I've got in the Lab 2 bank. Okay, now we've dashed the dot to form the equal voltage lines. We know that the electric field lines are perpendicular to the equal voltage lines. Now we want to draw the equal voltage line, through the equal voltage lines, the electric field lines. We're going to start on the positive and end on the negative. We want to make sure that all our electric field lines are evenly spaced. So you might want to start out in the center of the pattern and draw lines evenly spaced on both sides until you reach the end. The electric field is everywhere at right angles to the equal potential surfaces. They start on the positive charges, end on the negative charges. These facts can now be used to draw the field lines in the region where you have traced the equal voltage lines. So if you notice on the curve part, I come out, I have to be perpendicular, so I have to make sure whatever I do is a smooth path from beginning to end. In an idealized setting, the electric field lines would not be outside of those two lines, but in a real setting, they in fact are. And we want to always put the tip of our arrow toward the negative. Okay, now we want to complete the drawing, and we want to draw the electric field vector at one point on our plate, such that the change in voltage over the distance between the two lines is equal to our electric field. So you notice I chose the straightest path possible. I subtracted 3 volts from 4 volts, I got 1 volt. I measured the distance as 1 millimeter, so I had 100 volts per meter. And again, I indicated where the line is pointing. It's always pointing toward the negative. So you're going to have to make an electric field vector on each plate and carefully label them. You've got 2 lines, 2 points, a line and a point, the ice pail or the dot and the bucket. And you measure the voltage between the 2 lines, measure the distance. Voltage divided by distance gives you the electric field at that point. This is an example of how the equal voltage lines can be used to draw the electric field line. So in the case above, you have 2 lines. In the next case, you have 2 points, a positive and a negative. And in this case, you have a dipole, but it isn't shown on the 4 plates that you did. Okay, so this first plate are 2 lines. On the one that says CKD approved image for drawing, this is where you're going to draw your image. Notice I gave you what step 2 should look like, what step 3 and step 4. Your final drawing should be similar to step 4, only probably better. When you do your drawing, you're going to have to take a meter stick, and however much you enlarge this, that's your distance. It won't be the same for everybody because some of you will enlarge it to a full-size paper, some of you not. But these are 8.5 by 11 sheets, so you see every single step. And at the end, I want you to describe what it looks like. For 2 lines, it looks to me like a jail cell. Then here are 2 dots, and you want us to follow step 2, 3, and 4. You have a dot and a line, follow 2, step 3, and 4. You have a bucket and a dot. Now inside of the bucket, you notice there are no lines. That's because the voltage is virtually the same. The electric field inside a conductor is 0, which would mean there's no change of voltage. Do step 2, 3, and 4. And that's the lab. You want to do a write-up discussing what you saw and turn it in. This is not an Excel spreadsheet lab.